Hello everyone. In today's lectures we will see that what's the Eurasian lemma. In the last lecture we have seen that what is that uniform continuity on a metric space. So here we have the statement that let A and B are two disjoint subsets of a metric space x comma d. Then there exists a continuous real valued function or function f on x such that f of x equal to 0 if whenever x belongs to A, 1 whenever x belongs to B, and for everything that fx lies in 0 to 1. I am showing it by graphically. So if we have a metric space X, A and B are disjoint subsets of the X, then there is a function f from x to r, real number, so that every element of A goes to 0, every element of B goes to 1, and the rest goes in between 0 and 1. So we will prove this one, proof of the statement. As we know that the mapping, in the last lecture we have shown that the mapping x goes to d of x comma A is a uniform continuous function, and also the mapping x goes to d of x comma B also uniform continuous or uniformly continuous on x, or I can say simply the mapping, these two mapping are continuous on x. Given A and B are closed, I have just mistakenly written, let A and B are disjoint closed subset. Closed subset, this is the closed subset of A. There, this is closed subset, and this one is also closed. Given A and B are closed and disjoint, A intersection B is equal to 5. Now first of all I will show that I will show that the distance between x comma A plus distance between x comma B is greater than 0 for all x belongs to x. First I will show that claim that distance between x comma A plus distance between x comma B is strictly greater than 0 for all x belongs to x. Because if distance between x comma A, this is non-negative, this is also non-negative because distance function. The only way this is positive, that the only way this is positive is that the individual is both are greater than 0. Both are I need to show that the sum is greater than 0. This is only possible if one of them is positive. Okay, one of them is positive. If d of x comma A plus d of x comma B equal to 0 implies d of x comma A is equal to 0 and d of x comma B is also 0, because this is non-negative, this is greater than equal to 0, this is greater than equal to 0, and the sum is equal to 0. That means the individual must be equal to 0. ओके, जेहेतु इतार समेशन 0 है एंड दुईटा नॉन नेगेटिव है तो इंडिविजुअलटा बाध्य कर 0 है. अच्छा, आम लास्ट क्लास से देखी जदि डिस्टेंस बिटवीन x एंड e इज 0 इफ एंड ओनली इफ x बिलोंग्स टू a closer, means x belongs to a closer, and here x also belongs to b closer. But a and b are closed set. Closed means a closer equal to a, so x belongs to a and x belongs to b. Since A and B are closed set, so x belongs to what? A intersection B, but A intersection B is empty. So implies what? Distance between XA and distance between XB cannot be equal to 0. That implies distance between XA plus distance between XB is strictly greater than 0. Okay, why I have shown that distance between xa plus distance between xb is greater than 0. Let's see. Let us define a map. Let us define a map f from x to r by f of x equal to distance between xa by plus now listen carefully, as this is a continuous function and this is not equal to 0, always positive, so this function is defined. Again, this is continuous, this one is also continuous because sum of two continuous function is continuous, so I can say that fx is continuous. Here f is continuous on x since d of xa is continuous and d of xa plus dx plus b is continuous and d of xa plus d of xb is not equal to 0. This is not equal to 0. So upperta be continuous, tolata be continuous and not equal to 0. That's why fx is also continuous. Now I need to show the two things. Whenever x belongs to a, f of x equal to 0. Whenever x belongs to a, f of x equal to 1, and for the rest this lies in between 0 and 1. If x belongs to a, then we know that d of x comma a equal to 0. Hence ultimately fx is nothing but 0 by 0 plus d of xb, that is nothing but 0. If x belongs to b, then we know that d of x comma b is 0. Hence f of x is nothing but d of x comma a by d of x comma a plus 0, and that is nothing but 1. So it is clear that whenever x belongs to a, fx equal to 0. Whenever x belongs to b, that f of x is equal to 1. For the rest, for all x belongs to x, listen carefully, fx is nothing but what? D of x comma a plus d of x comma a plus d of x comma b. I need to show that this is always positive and this is greater than less than equal to 1. Since this is always greater than equal to 0, this one also is greater than equal to 0. So this is strictly greater than equal to 0. Again, f of x can be written as d of x comma a plus d of x comma b minus d of x comma b by d of x comma a plus d of x comma b. Just I add this and subtract this. This is nothing but 1 minus d of x comma b by d of x comma a plus d of x comma b. Since this is always greater than equal to 0, so 1 minus something positive on 0 is always less than equal to 1. Hence for all x belongs to x, fx lies in between 0 and 1. That's the Eurasian's lemma, and that is very important. Okay. So next we have some results over the continuity function, uniform continuous result. A continuous function may not map a Cauchy sequence to a Cauchy sequence. So there is a result, short result, a continuous function may not map a Cauchy sequence to a Cauchy sequence. We will give it by an example. Example, let f is a function from 0 infinity to r defined by f of x is equal to 1 by x. Here f is a continuous function on 0 infinity. Let xn is equal to 1 by n in 0 infinity. Now xn is a Cauchy sequence, okay, which can be shown easily. Now xn, if xn is equal to 1 by n, is a Cauchy sequence. To show it is a Cauchy sequence, just need to show that. I am not showing here. Xn plus p minus xn is less than epsilon for all n greater than equal to p, and for all n greater than equal to m, and p greater than or p belongs to the natural number. Or simply you can take xn minus xm is less than epsilon for all n m greater than equal to some k. This can be shown easily. Now xn is a Cauchy sequence. Now f of xn is nothing but f of x is 1 by x. So this is 1 by xn, 1 by n, that is nothing but n. So what we have, that f of xn is nothing but n, which is an unbounded sequence. 1, 2, 3 is a, which is an unbounded sequence, which is an unbounded sequence, implies f of xn is not a not a Cauchy sequence. Okay, so here we have seen that a continuous function cannot map a Cauchy sequence to a Cauchy sequence. So we have another result over the uniform continuity, was that I'm just writing. So here we have the statement that x comma dx and y comma dy be two matrix space, and f is a function from x to y which is uniformly continuous on x. So if we have xn is a Cauchy sequence in x, f of xn is also a Cauchy sequence in y. That means a uniform continuous function maps a Cauchy sequence to a Cauchy sequence. Okay, we will prove this one. Proof. We have given two things. Here f is a uniform continuous and xn is a Cauchy sequence. Given f is uniformly continuous on x, that means for every epsilon greater than 0 there exists a delta positive such that the distance between f of x1 f of x2 strictly less than epsilon for whenever distance between x1 and x2 is less than delta in x for all x1 x2 belongs to x. Again, given xn is a Cauchy sequence in x, that means for a given delta greater than epsilon, in place of epsilon I will take this delta which is obtained in the first case. আমার যেন delta ভারী છે, I will choose that delta as epsilon for the Cauchy sequence. Given greater than 0, delta greater than 0, there exists a term k belongs to n such that after the kth step distance between xn and xm is less than delta for all n m greater than equal to k. Since the distance between these 2 points is less than delta, so as per the uniform continuity result, whenever distance between 2 points is less than delta, then the distance between their image point is less than epsilon. So here we can say that the distance between f of xn and f of xm is less than epsilon for all n m greater than equal to k. Okay, so this shows that f of xn is a Cauchy sequence in y. So here we have the result. So a uniform continuous function maps a Cauchy sequence to a Cauchy sequence. Thank you.